Hello, this is another video under Engineering Mathematics. Still we are talking about matrices, and today I'm going to talk about the determinants. So let's have an direct introduction to determinants, and I'm going to give a brief definition for determinants. In linear algebra, the determinant is a scalar value that can be computed from the elements of a square matrix and encodes certain properties of the linear transformation described by the matrix. This is actually something that we might encounter whenever that we are dealing with linear algebra, which is something that we are not covering in our course. But anyway, you just need to know that determinant is considered to be a scalar value that we can obtain from any matrix, from a square matrix, and as it says here, it encodes a certain properties. So certain properties means that there are some properties and characteristics stored in this value, which is the scalar value, the determinant. Okay, and it has something to do with linear transformation. Okay, linear transformation of the matrix, which is something that commonly used in linear algebra. The determinant in general of a matrix A is denoted by determinant A, as you can see, det A or determinant A, or we put it between two sticks, something like this, and do not get confused that it does not mean absolute here. Okay, it is the determinant. It is just a kind of how we represent the determinant. Geometrically, it can be viewed as the volume scaling factor of the linear transformation described by the matrix. As we said, it is a kind of a scalar value, and this value we can view it as the volume scaling factor of the linear transformation. Okay, volume scaling factor of the linear transformation described by this matrix. Okay. I will not go deeper into this understanding because there are a lot of graphical representation you can find on YouTube regarding what is the meaning of determinant, and they are very attractive. So anyway, just remember that it is scalar value. We use it in order to encode certain properties of the linear transformation, and we can put it like this. It is the volume scaling factor. That's it. The volume scaling factor of the linear transformation that is described by the matrix. Okay, now let's go now to what are the properties of determinant. What are the properties of determinant? So if we have A, which is like square matrix n by n matrix, then the determinant of the transpose of the matrix equal to the determinant itself. Okay, and this is something sometimes we use it in our calculations. And if this matrix, the original matrix, has a zero row or column, so if we have like zero row or a zero column in our matrix, then the determinant should equal to 0. We're going to see this when we are going to work some examples. And 3, if B is formed from A by interchanging two rows or columns, if you remember, this is changing the rows, it is type 1 operation. Okay, type 1 operation for interchanging two rows. Okay, type 1 operation. Then the determinant of B would equal to the negative sign of the determinant of A. Okay, and number 4, if two rows of A are the same, if we have two rows or we have the same two rows in one matrix, or if two columns of A are the same, then the determinant of this matrix should be 0. Okay, the determinant should be 0. And property number 5, if B is formed from A by multiplying a row or column by a non-zero number, which is alpha, we call it the type 2 operation, then this determinant of the matrix B would equal to alpha times the determinant of matrix A. And property number 6, if one row or column of the original matrix A is constant multiple of another row or column, then the determinant is going to 0. Take care of this. Determinant was 0 here in this property number 4. If we have two rows or two columns to be the same, and if we have multiple constants of a row, if there is one row that is considered to be a constant multiple of another row or a column, then the matrix is going to be, the determinant is going to be 0. Okay, another property, which is, suppose that each element of row K of the matrix A is written as the sum of this. If we say that we have determinant of the matrix K, if we have a matrix, and this matrix, it is having in each element, all the elements, like they can be described like this: one element plus another element. Then what we want to get from this property, that this matrix A, it would equal, the determinant of matrix A would equal to the determinant of matrix B plus the determinant of matrix C, where B and C are going to be formed. This is B. This matrix B is going to be formed by changing each element in matrix A by BK only. So here BK1, for example, here would be BK. And plus matrix C, this is the matrix C, the determinant of matrix C, that is coming from the matrix C after replacing all the elements of matrix A by CK, which is here, for example, it was CK1 if we are talking about this specific element. So this means that the determinant of a matrix would equal to the summation of two determinants of two different matrices if the elements of these matrices are being summed up in the main matrix. Okay, if the matrix A, every element in matrix A can be divided into two elements, one in matrix called B and another one in matrix called C. Okay, now let's go to the next one. If D is formed from A by adding alpha times one row or column to another row or column, which we call it type 3 operation, if you remember this, then the determinant of D would equal to the determinant of A. Take care of this because it's very important. We are going to use here alpha times one row and add it to another row. So in this case, the determinant of D would equal to the determinant of A. It's a very important property. So the type 3 operation does not change the determinant. Does not change the determinant. But if you go back, if we are going to have type 1 operation, if you remember, it changes what? Yes, the sign. It changes the sign. Type 2 operation, we are going to have the scalar value that we use here. Multiplication of a row by a non-zero number, alpha, then the determinant will be changed. However, if we are going to talk about type 3 operation, it is going to be the same. So alpha, by adding alpha times one row or column to another, this would not change the determinant of D. It will be the same as A. Property number 9, A is non-singular, and you understand what is the meaning of non-singular now if you watch the previous video. A is non-singular if and only if the determinant of A does not equal to 0. So this is another significant characteristic for important characteristic based on the determinant of the matrix. And property number 10, if A and B are both n by n, then AB, the product, the determinant of a product, is the product of the determinants. Okay? So the determinant of the product is the product of the determinants. That's a very important characteristic that we're going to face if we are going to work some examples. Okay? Okay. Now we can go to how to evaluate the determinants. How to evaluate the determinants. And we are going to use method 1. There is a method here. There are different methods for evaluating or for the evaluation of determinants. We are going to use the first one of them. Simply, in this evaluation method, we want to put a rule here that if we have a 2 by 2 matrix, the determinant of the 2 by 2 matrix is like multiplying if we have A22, A23, A32, A33. This is any matrix with different numbers, as you can see. The determinant of this matrix is going to be the multiplication of the diagonal here, this diagonal, minus this diagonal, which is A22 times A33, which is this one, minus A23 times A32, as you can see here. Okay. This is supposedly to be something that we should remember, that for any 2 by 2 matrix, which is the smallest matrix that we can see, if we have it with the elements, as you can see, A22, A23, A32, and A33, for example, then the determinant of this matrix simply is going to be A22, A33, which is the diagonal here, minus A23, A32. Okay, this is the determinant of it. Okay. If we are going to evaluate other bigger matrices, then we try to reduce the amount of work, okay, or the volume of work and volume of calculation by introducing 0 elements at one row, for example. Okay, so here the determinant of this matrix is going to be like this, that we look to the row that is containing zeros, and we are going to pick one non-zero element or non-zero value, and then we are going to exclude the column and the row, and then we are going to multiply this element, which is A11 here, by the determinant of the remaining matrix. So the determinant of this matrix, which is matrix A, would equal to A11 times the determinant of the smaller matrix, which is the square matrix here. This one, as I said to you, it is easy to be evaluated. The determinant of this 2 by 2 matrix easy to be evaluated. So we can obtain this determinant of a matrix by trying to find 0. The more zeros that we have in one row, the less calculation that we are going to have. Okay, so now the strategy is how we are going to make these kind of, or add more zeros here. Okay, so this is what we are going to explain. And actually, this is we have explained before when we were making, if you remember, the elementary row operations and column operations. If you remember that we were talking about how to change the value of certain elements. We are going to follow the same strategy here. Okay? Okay. We can put it in something like this. This is a kind of like theory for what I have explained here. So let A be n by n matrix, and suppose row K or column R has all 0 elements except for one element, which is AKR. It was A11 here in this example. Then the determinant of the matrix is going to be minus 1 raised to K plus R, where K, it is related to the row of the number or of this element, and R, it is related to the column of this element, times the element value, which is AKR, it was A11 here, times AKR. What is the meaning of AKR? It means that the reduced matrix, not reduced, the matrix that is going to be formed by removing row K and column R from the original matrix, and the remaining one is going to be AKR. Okay? So this is where AKR is the n-1 times or by n-1 matrix formed by deleting row K and row R of A. How we are going to do this? I think that it is the time for an example. Okay, so do not worry, the example would show it to you. Here we have a matrix. This matrix is 4, 2, minus 2. Actually, this is minus 2. Okay, it is. I think there's something wrong was in the book. And here 3, 4, 6, and 2 minus 6 and 8. So our strategy is going to be something like this: that we will choose any row, or any column, anything, any row or any column. Let's assume that we're going to assume this column, for example, which is the middle column. We are going to change this element and this element to be zeros. And then we are going to evaluate the determinant of this entire matrix. Then the question is how we can change this 4 and minus 6 to zeros. We are going to make some column operations. Okay, it is similar to the row. It is also similar to the row operations. Sorry, we are going to make row operations in order to change this to be 0 and this is to be 0. So look here, we have 4 here. If I multiply row 1 by minus 2 and add it to row 2, then we are going to get rid of this 4 and we will obtain 0, right? So this is the first row operation. Minus 2 times row 1 plus put it in row 2. This is what I said. And here for minus 6 we're going to do the same. We are going to multiply row 1 by 3. So row 1 multiplied by 3 and add it to row 3. So we will put it in row 3. So 3 times 2 plus minus 6, it is going to be 0. So we're going to obtain it 0 here. The new matrix after row operations, it is going to be the first row, it is the same. However, the second row, it is going to be minus 5, 0, and 10. And the third row is going to be 14, 0, and 2. Okay? Take care that minus 4, minus 5, and 14, they are different than the original matrix after making the row operations. And 10 and 2, it is different than 6 and 8 here because we have done the row operations. Right? Now we are going to exploit the zeros in all but. So we're going to apply our theorem here. Okay? Do you remember that we said that when we make the change in row operation, elementary row operation, there is nothing will happen. So the determinant of this matrix, which is A, it is going to equal to the determinant of this matrix, which is B. Why? What is the reason? If we go back 2-3 slides before, you will find that row operations does not make change in the determinant. Okay? Then, in this case, we are going to apply our formula, which is, this is the formula here. Minus 1 times K plus R times AKR multiplied by the reduced by the AKR, which is the small sized matrix. So we are going to choose 2 to use it as our element. Then, so we're going to say the determinant of A equals to the determinant of B, and it would equal to minus 1, which is constant in the equation, to the power, this is row 1 and column 2. So we're going to add here row 1 plus column 2, right? Okay, times the element that we are talking about, which is 2. So we're going to put 2 here. Then the determinant of the remaining part. The determinant of the remaining part. We're going to remove this row and this column. So the remaining is minus 5, 14, 10, and 2. It is something similar to this. The determinant of minus 5, 14, 10, 2. The determinant of this. Now we know the determinant of this matrix very well, right? We can multiply the diagonals and subtract and then multiply by 2 times minus 1 raised to the power 1 plus 2. And this is exactly what we have done here. Minus 1 raised to 1 plus 2 times B12. What is the meaning of B12? It is the original matrix A by removing row 1 and column 2. That's the meaning of this. So B12, it is this matrix by removing row 1 and column 2. Then the remaining is going to be here, minus 5, 14, 10, and 20. So we call this B12. B12 means that the original matrix after removal of row 1 and column 2. That's the meaning here. If we calculate, you are going to find that the determinant is 300. Okay, that's the case here. This is a very huge matrix. Okay, I can leave it for you to investigate, but we are going to make something. We want to get the determinant of this. So actually the determinant here is going to be in like a chain rule. This means that first of all we are going to look to one column which is having zeros and try to put all of them to be zeros. For example, here this column, it contains 0 here. Then we can change this and this and this to be, these values to be zeros. How we can obtain this? We can obtain it by row operations. I will leave it to you to make the row operations. I put here the operations, the procedure. Okay, for example, this is only for your example. In order to get rid of this 2, to make it 0, we're going to multiply row 1 by 2 and add it by minus 2 and add it to row 3. So minus 2 times row 1 plus and add it to row 3. So we will get 2 to be 0. Similar for 5, we're going to make it with this. Minus 5 times 1 plus 4, it would give us 0 here. Similar for this, it is 3 times row 1 plus 5, it will give us, yes, plus 5 means row 5, then it will give us 0 here. So we will get this equation. Look to this matrix. This is a new matrix, which we call it B, after some elementary row operations. Okay? So as you know from the previous theorem, adding a multiple of one row to another does not change the value of the determinant. As I said to you, it was very important properties, one of the important properties of the determinant. So the determinant of A is going to equal to the determinant of B. Now the determinant of B is going to be easier a little bit. Why? Because we are going to we're going to apply our rule, okay? Then we're going to pick this element 1, minus 1, and put the row and the column, row 1 and column 3, raised to the power 1 plus 3 times the element value itself, which is 1, times the remaining matrix C. The remaining matrix C, it will be formed by removing of column 3 and row 1. So it is going to be, this is the remaining part here and here. This is the remaining part. So this is C actually. So we're going to find minus 1, 5, minus 1, 20, 30, minus 17 here. 5, 3, 1, 15, 5, 3, 1, 15. And on the right hand, 1 minus 5 minus 18, 18. And 7, 3 minus 8 and 10. So now we have this matrix. Now this matrix is less complicated than this one, right? We're going to make the same strategy here, not the same row operation exactly. It will be something similar to this. We are going to pick any column. You can do it with any column. okay, with any column or any row, and try to make the one element to be non-zero and the other elements to be zero. For example, we have chosen row number 1. We kept this element to be -1, and then we did some row operations. I will leave it to you. You can follow it exactly, and you can get zeros at the first row except the first element. Then we are going to obtain D, which is the matrix or the determinant of D. -1, this element is -1 raised to row 1 plus column 1. 1 plus 1 times -1, which is the element itself, times another matrix, which is E. It is the reduced matrix. The reduced matrix is going to be formed by removing this row and removing this column. The remaining matrix is this. This is E, which is, as you can see here, this matrix is this matrix. Okay? Okay. Now we are going to make the same. We are going to check. We are going to move or make the same by making these two elements to be 0, and this element we are going to keep it as it is. Okay? Then we are going to make some row operations. So we are going to add -15. This is not -1, it is -15. As I said, it is a kind of mistake in the book. Okay? So add -15 times row 3 to row 1 and -12 times row 3 to row 2 to get, we are going to get, this is another row, another matrix, which is reduced 1. We are going to use this element for our evaluation of the matrix determinant F. -1 raised to, this is 1, 2, 3, row 3 and column 2. Row 3 here and column 2 times 1, which is this element, times the remaining part, or the remaining is, as you can see, it is 1153991 here, 11778 1510 here. This is G. This is easy for us now to calculate, right? It is a determinant. This is a 2 by 2 matrix, which we can determine its determinant very easy. Now this is the determinant. Okay. Okay, working back through the chain of determinants that we have had before. So we have A, it equals to the determinant of B. However, C, if you remember here, we have this determinant C, okay, and we have the determinant D, okay, we have the determinant D, but we have make some these operations that we have obtained because we added multiple of one column to another. Then the determinant of C would equal to the determinant of D. Okay, and then after that we are going to obtain the determinant of D to be equal to the D minus, take care, minus the determinant of E, minus the determinant of E. And then minus, because we have like some row operations and we were like multiplying by constant. So in this case we are having the minus here. Okay, and then this is for F, and then E would equal to F, and then we are going to end with G. Okay, and at the end we are going to end with the most easiest part, which is the determinant of G. This determinant of G is going to be the final value for the determinant. So the very complicated determinant that we have here, which is very complicated matrix that we have, we ended up with a very simple one to calculate here. How we did so? It is based on the chain of the operations of row operations and so on. Okay, you can go through this example again because it's really very fruitful for you. if you are going to go through it, you are going to find that it is easy for you, but it will train you how to obtain the final determinant. Okay, now it is in-class assignment for you. So these are the determinants. Please stop it here and try to work the determinant based on what you have learned in this class. Okay, I'm going to provide for you the answers. Okay, so the answers for the three kind of examples, we are going to work them. You are going to make these row operations, and again you can do it for any row or for any column. Okay, no need to follow my strategy here. Only what is written here, it is I put only in the middle column 0 and 0 in the top and bottom, and then we have 1 here. So then we evaluated the determinant to be these values for the three examples. Okay, you can work them and you can find the determinant. Okay, now let's go to another way for evaluation of the determinant. We call it expansion by factors. I'm going to read only the 3 lines, and then I'm going to give example directly to understand how we can make or evaluate the determinants using expansions. In the preceding section, we evaluated determinants by using row and column operations to produce rows and or columns with all but one entry, which is one entry is going to be non-zero and the others are going to be zeros, right? So we are going to make it easier for our calculation. In this section, we exploit this idea from a different perspective to write the determinant as a sum of numbers times smaller determinants. So we're going to follow like similar way, but a little bit different than before. We call it expansion by factor. I'm going to jump into the theorem. I want you to just bear with me and go through this theorem now, and the application of the example would really make it easy for you. The point is, we are going to make expansion based on what we call it cofactor expansion by a row. We have 2 methods actually here. We can choose, if we have a matrix and we have like different elements, we can choose one row and then we can evaluate the determinant based on this row. So we call this cofactor expansion by a row. How we can do it, I'm going to explain it in a minute. Okay, this is the rule. Another way is cofactor expansion by a column. Then we're going to find a column, any column. Let's assume this column, for example, and we are going to use it as a basis for the determinant evaluation. So these are what we call it the cofactor expansion of a column. Now let's go to this cofactor expansion of a row and understand the theorem briefly, and then we're going to explain using the example. So the determinant of the matrix is going to be based for any k, which k means that for any row within 1 to n, any row, okay, the summation of the summation of the following from j equal to 1 to n for all rows, it is going to be minus 1 times raised to the power k plus j times the element itself times the matrix mkj. Okay, this is the theorem. Okay, I will not explain now what is the meaning of akj, mkj, what is k, what is j. You're going to understand it directly from the example. So let's have the example, and then I will revisit the theory again. Let's assume that we have this matrix, which is minus 6, 3, 7 in the first row, 12 minus 5 minus, this is minus 9, this is minus 9, this is another mistake in the book, I call it minus 9. And here 2, 4, and minus 6. Okay. We are going to make the expansion now using the cofactor, okay, or cofactor expansion using the row. So we are going to expand it using the row. We're going to use the first row. Okay? So please concentrate with me what we're going to do. First of all, this matrix is what by what? It is 3 by 3, right? Then we're going to make the summation from j equal to 1 to 3. Okay. The summation of -1, it's a constant, raised to 1 plus j. 1 plus j. What is 1 plus j? We are going to, this is row 1, right? This is row 1. So we are going to use every element in this row in order to expand and make the expansion of the determinant. For example, I'm going to use -6 first. Okay, so it is going to be like this. -1, this is the first one, which is -1, it is constant, raised to 1 plus 1. This one, it is the first column, right? And then I'm going to use another element, which is 3. Okay, this is plus. I'm going to explain about this now. Okay, and then plus -1 raised to 1 plus 2. It is column number 2 times the element number 2, which is 3. And then in the third term, where I'm going to put -1 raised to the power 1 plus 3, which is the column number 3. And the element is 7. So now we have like 3 different terms. The first value, which is -1 to raised to the power, it is, we understood now, it is based on the location of each member. And then we're going to put here the element value, which is -6. Here it is going to be 3, which is in the second column here, 3. And here it is 7, which is the third element in the row, which is 7. Okay, now we understood what is the meaning of -1 raised to 1 plus j times aij, which is a1j here because we use the first row. Okay, now what is the meaning of m1j? It is going to be formed by looking to the matrix here. This is our matrix. Okay, let me clean everything because I think that it's really chaos. Yes, here. Here we have -6. So we are going to eliminate this row and this column. Eliminate them. What is the remaining? -5, -6, 4, and -6. Here. -5, -9. I'm sorry, this is, as I said, it is -9. Huh? Okay. And -9, it is 4 and -6. 4 -6. Okay. And the second term, we are going to make, let me clean it. So in the second, we are going to remove this column and this row. We are going to remove it. Then the remaining is 12, 2, -9, and -6. 12, 2, -9, and -6. Understand? And let me clean here. And then the third one is going to be removing this column and this row. So we're going to have 12 -5, 2, and 4. 12 -5, 2, and 4. That's it. This is how we can determine it. Now everything is known for us. We can calculate this very easy, and this one, it's very easy for us. It is the 2 by 2 determinant, which is very easy for us to calculate. Then we can obtain this as the determinant to be 172. Okay, now let's clean this in order to verify for you that it is going to be the same. Let's expand our and calculate our determinant using row 3 instead of using row 1. So we're going to use this row. Okay, it is a similar fashion also. We're going to make the same. So we are going to have 2, 4, -6. So for 2, here, this is 2 here. This is 2. And now we have -1 raised to the power. It is row 3, column 1. 3 plus 1 times 2, which is this element, as we said. Times, we are going to erase this column, this row, and this column. Then we are remaining with 3, 7, -5, and -9. 3, 7, -5, and -9. Okay, clean. And then we're going to make the same for element 4. This is element 4 here. This is the element that we are going to have. And it is row 3, column 2. So it is 3, 2 here. Minus 1 raised to 3 plus 2. And element 4 as it is. And then remove this column and remove this row. Remaining is minus 6, 12, 7, minus 9. Minus 6, 12, 7, minus 9. And similar for, let's clean. This minus 6, it is going to be, as you can see it here. This is minus 6 and the same as we have done. If you repeat this, please calculate it by yourself. You're going to find that the determinant is 172. It is exactly as we have done when we expand using row 1. So if you use row 1 or row 3 or row 2 or column 1, column 2, column 3, as we are going to see in the next slides, they are the same. The determinant is the same. Okay? Now I think you understand the theorem, this one. Let's go back. Now I think that you can define the theorem by yourself. You understood it using the example. So I'm not going to explain this kind of blah 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 here, because really it has no meaning if you already have understood this example. Okay? So I think this is the best way for you to understand the meaning of the theorem using the example directly. Okay, now let's go to the next part, which is making the same, solving the same determinant, the same matrix, evaluating the same matrix, but using columns instead of rows. I think that without reading the theorem, no need to read the theorem, you're going to understand it from the example. Let's have the same example that we have. In the column, we are going to use any column. Okay? Let's assume that we're going to use column 1, for example, which is this column, minus 6, 12, and 2. So now we're going to put minus 6 here, 12 here, 2 here. Okay. And now, minus 6, it is having row 1 and column 1. So 1 plus 1. It's going to be 1 plus 1 here. 1 plus 1. This is minus 1 raised to 1 plus 1. For this element, which is still 12, it is row 2 plus column 1. So it is going to be 2 plus 1 here. That's right. And for this element, it is going to be row 3 plus column 1. So it is going to be row 3 plus column 1, as you can see here. And the element is 2. Then the determinants, or the remaining, it is easy. I think you can understand now. For element minus 6, this one, we're going to remove this element, this row, and this column. The remaining is minus 5, minus 9, 4, and minus 6. Minus 5, 4, minus 9, minus 6. Let us clean here. For element 12, remove this row and remove this column. 3, 7, 4, minus 6. 3, 7, 4, minus 6. And let's remove this. And for 2, we're going to remove this row and this column. So 3, 7, minus 5, minus 9. 3, 7, minus 5, minus 9. So now we understand how to make it. Now you can evaluate this, these terms, these 3 terms easily, and you can obtain also the same value, which is 172. Okay, 172. Now this is easy for us. Now we can assure that using row expansion, or using column expansion will give the same amount or the same value of the determinant. So it is no problem at all which kind of cofactor expansion using column or row that you are going to use. Okay? Okay, this is in order to use column 2 instead of column 1. I think that I'm going to leave it for you. You will understand it, and I hope that you can do it by yourself. Okay? Now it is the time for the home assignment for you. I'm going to leave you with these 3 determinants. So evaluate the determinant using cofactor expansion of a row and again by a column. So you're going to make it 2 times. 1 time by a row and another time by a column. You can choose any row, you can choose any column, but the determinant should be the same at the end. Okay? You are having these 3 examples. Okay? Thank you very much for watching the video, and I hope that you have understood it well. And thank you, and see you in another video.